Hey there, Pre-Calc kids. Today we are looking at rational functions and their properties. Alright, so polynomial functions are seen as functions with integer powers that are non-negative. Alright guys, we're going to look at how do we deal with the denominator? What makes them rational? What restricts our domain and range based on division by zero? Let's get to it. We are going to define any rational function as any r of x. R stands for rational. Let's be rational about it. Where we have our numerator of x divided by our denominator of x. Where d of x cannot equal 0 because we can't divide by 0. If you don't believe me, grab a calculator and try it. See what happens. Alright. That shouldn't be new, but this is kind of going to be some notation we're going to talk about. Let's see how this affects finding domain. Now, when we find the domain of this beast, we kind of introed it before, but now we're going to get into detail on some find domain with rational functions. Now our top, there's nothing that restricts us on the top, right? I can plug anything into x plus 3 and it's fine. So I don't worry about that with domain. But what I do know is x squared minus 8x plus 12 can't equal 0, right? So I'm going to solve this like a normal problem. So I'm going to factor it. And it factors into x minus 6, x minus 2. Can't equal 0. So 6 and 2. X can't be. That makes sense? Because if I plug in 2, I get 0 on the bottom. And that's no good. If I plug in 6, I get 0 on the bottom. And that's impossible. So, our domain, what if the top's non-restrictive? There's nothing I can't plug into the top. But this bottom can't be 2 or 6. So when I think about this, I start at negative infinity. I'm going to go to 2. Now at 2, I can't be equal to 2, or else I'll break the matrix. So I'm going to jump over 2, and then I can go up to 6. Can't be 6, because I can't have a 0 in the denominator. And then I'm going to go from 6 to infinity. Right? Because I can't equal 6, can't equal 2. Square roots, we put the bracket because you can take square root of 0. Now, what's happening at 6 and 2? Well, if x can't be 6 and 2, that means these are going to be some sort of vertical asymptote. Okay? Keep that in the back of your head. Okay? You may have done something with this last year in Algebra 2. More than likely. Okay. Alright, y'all. We have a lot of notation to go through. I'm going to do my best to describe this. We're going to use it a lot. First one we're going to look at is we're going to see this is x, arrow, a, negative. Notice that negative is behind the a, not in front. What this is stating is x, in orange. The arrow means approaches. A, now that negative on a graph, negative is on the left side, right? If I ever draw it, xy coordinates, over here is negative infinity, right? So that negative says, as x approaches a from the left side, from the negative side, okay? Whereas this one would be x approaches a from the right, and the right being the positive side, okay? These ones aren't really new. X approaches infinity, x approaches negative infinity. Either it's going up or it's going down, right? We've been dealing with that one. Now, if it's f of x is approaching a, now remember, f of x is associated with our y value of the function, okay? So as x approaches infinity, we're thinking of the graph going to the right. F of x to infinity, we're thinking of the graph going up, okay? We're going to do a lot of practice with these, so if you're feeling a little fuzzy now, it only gets worse. No, I'm joking. Let's just do some examples. That'll help us more than reading this over and over again. But keep this page handy. It's a nice little tool where if you see this notation, you can go back and look at it. So, let's look at this graph and find vertical asymptotes and then describe their behavior as they approach said vertical asymptotes. Alright, so first things first, I gotta turn my Moby back on. I was letting her charge. Good girl. So, the graph will approach vertical line either increase or decrease without bound. That is, if I have a vertical asymptote of x equals a, then my limit as x approaches a from the left side, as I approach that a value, will be either positive or negative infinity. An asymptote means it's going to go off to either positive or negative infinity, and from the right side it'll also be positive or negative infinity. So our example on this graph, our vertical asymptote is at x equals -3 is our vertical asymptote. I'm going to use VA a lot, vertical asymptote. So, my limit as x, wow, that's some infinity right there. As x approaches -3 from the negative side. So as I approach from the left side, does my function go to positive infinity or negative infinity if I start on the left? I heard that it goes up to positive infinity. Oopsie. Now, what's my limit as x approaches my asymptote, which is -3, from the positive side? So as I come from the right side is the positive side. I'm starting on the right side, does it go up or down? Down to negative infinity. Okay? Now, horizontal asymptotes are a little bit different. So we're going to use a different color. Let's use green. Good old Barney. So we're going to call our horizontal asymptotes our y equals b. Now, as we approach our horizontal asymptote, our x will tend to go off to negative infinity or infinity. I'll show you what that means. In this graph, we have a horizontal asymptote at y equals 2, correct? So that means on this graph, as I go to negative infinity, now remember that negative is in front, so as I go to the left, this graph goes to our horizontal asymptote, so it's going to be equal to 2. And now that's also going to be true since it's a horizontal asymptote. As I go to positive infinity, as I go to that right side, my graph is also approaching 2. Okay? So you approach the horizontal asymptotes as you go to infinity. And when you approach your vertical asymptotes, they go to infinity. Test tomorrow. No, I'm just kidding. We'll take our time. We're going to spend a lot of time on this, okay? It's an important concept. All right. So there's going to be 3 cases to look for asymptotes. This is actually one of my favorite things about this because it works out nicely. If we're dealing with rational functions, if the degree of our numerator, our top, is less than the degree of the denominator, the line y equals 0 is the horizontal asymptote. So for example, if I give you y equals 3x squared minus 2x over 6x to the third minus 4. That's a lot of stuff, but we can look at it and find our asymptote pretty quick. I look at my highest power of x on both, right? The degree of my numerator is only 2. The degree of my denominators is 3. So because my degree on top is smaller, I know that y equals 0 is my horizontal asymptote. The reason that is, as we plug in bigger and bigger numbers, the bottom gets bigger faster. So this is going to become a really, really small fraction the bigger the number we plug into it. Now, if the degrees are the same on the top and the bottom, then we take the ratio of the leading coefficients, and it's going to be equal to A over B. The better thing to do on this is to look at an example. Suppose I had 4x to the fourth minus 2x over, let's do 12x to the fourth plus x cubed plus 1. Doesn't matter. So when I look at this, the power that's larger takes control of the situation. They get bigger faster as we go to infinity. So this is my biggest power, and this is my biggest power. This stuff in the back does nothing to my end behavior, so I don't worry about it. So for this one, my horizontal asymptote would be equal to y equals, well, my leading coefficients, 4 over 12, or 1/3. Okay? It's not as it's not as bad as it looks, but it looks as bad as it is. All right. Now, if the degree of the top is greater than the degree of the bottom, that means it has no horizontal asymptotes. So if I give you like x to the fifth minus 3x squared plus 1 over x minus 2. When I look at my largest, or my degree of each, top is degree 5, bottom is degree 1, so there is no horizontal asymptotes on that one. Okay? Okay. All right, y'all, let's look at some examples. So, find the horizontal asymptote for each of the given functions. So remember, vertical asymptotes, vertical, we set the bottom equal to 0 and find out when it is 0, and that will give us the vertical asymptotes. Horizontal, we got to use these 3 cases. So on A, my top power is x to the 0, correct? 0 degrees, because it's a constant. The bottom is 2, because it's x squared. So my top is less than the bottom, right? Now if our top is less than the bottom, according to my chart, my horizontal asymptote will be y equals 0. And that's my reason. For B, I take my degree. They both have a degree of 1, right? X is the same as x. If they're the same, we use our leading coefficients. So y would be 3 over 1, or 3. That'd be my horizontal asymptote, because they have the same degree on the top and the bottom. On C, my top power is x squared, which is greater than x, right? When our numerator is bigger than our denominator for degrees, then we have none. No horizontal asymptote. No laughter. Like my jokes. All right. Okay? Okay. Now, what if there is a slant or oblique asymptote? These are a weird one. Okay? So, this is going to be a case in which our top power is bigger than our lower power, but there is a slant asymptote, and I'm going to show you kind of what that looks like. We're going to do more with slant asymptotes in a day or two, okay? We're going to do a whole thing on it. Okay? Okay, Mr. Tooler. Thanks, guys. So what I'm going to do is to determine it, we need to long divide this out. But luckily, this bottom is just x plus 5. Because of that, I can synthetically divide it out and do a quick little reminder. To synthetically divide, we put down all our leading coefficients of our top function, right? And up in this box, we don't put positive 5. We put negative 5, the opposite of it, right? Then we start by bringing down the 1. Then we do 1 times 5 is negative 5. I multiplied that number we brought down by negative 5. I'm going to combine those, get negative 11, right? I'm going to do negative 11 times negative 5 is 55. 55 plus 7 is 62, and that's a remainder. And do what we do with that remainder? We ignore it on these, okay? We ignore it. Because we aren't looking for like an actual function. We are looking for a slant asymptote, okay? We just use this part. So that's going to be a negative 11 nothing, and then a 1x. Because go through and you can do your x squared. So our oblique asymptote is y equals x minus 11. We just divided it out. Again, we're going to do more with this later, so don't freak out if you don't understand why. We'll go into that in a little bit. Aight? Aight. Sorry for the jarring jump cut here, but I'm going to go right into how to analyze rational functions. So when we analyze rational functions, the first thing we have to do almost every time is simplify it. Okay? Now, when we simplify a rational function, that first step is factoring it. And it's unfactorable, then we don't factor it. But we factor it into its most broken down form. We find the zeros of the top and the bottom because zeros on the top are going to be x-intercepts where it crosses. Zeros on the bottom are going to be vertical asymptotes. So we still need the zeros of the top and we need the zeros of the bottom. Now what's interesting, if the zero is common and it cancels, that is a hole. That means you can't see it by graphing it. The only way you can see it is by factoring it and seeing if they cancel. So again, we're going to be doing a lot of the same stuff over and over on these problems, but we'll get good at it. Okay? So let's see what it means. Oops, I want to do this. I want to work it out. So we're going to analyze this rational function. Do a full walkthrough. We're going to find x-intercepts, vertical asymptotes, and holes. All right, now my first step, what I want to do first is do what? First, I'm going to factor. So the top, I'm going to pull out an x. That's going to become x times x minus 3. My bottom, what can I pull out? a 3x. So I'm going to do 3x times x plus 2, right? Now, these x's are going to cancel, right? But I'm going to remember them. I'm going to remember that. All right? I need to remember that those cancel. It's going to come up later. Okay? Well, actually, I'll just tell you guys now. Because those x's canceled, what that means is at x equals 0, because I set my equation x equals 0, there is a hole in the graph. And we taught, because if they're the same, if we factor and the top and bottom have the same 0, that's a hole. Okay? All right. Now, how do I find out where that hole is? I can take that 0. If I take that 0 and I plug it into this function, you get 0 over 0. That's no good. I'm going to plug it into my simplified form. And when I plug in 0 into that graph, I get negative 3 over 2, right? So the hole in the graph is actually at the point 0, negative 1.5. Okay, I'm going to do more examples of this too when I get back. Just do your best today. Your teacher there will help you, hopefully. Now, we need to find out some more stuff. And this gave us holes. How do we find an x-intercept? Well, we set the top equal to 0 and solve. All right. Now we know that factor. We already have it factored, so I didn't have to write it like that. I'm just showing you where it came from. Now, the first 0 of x equals 0, we're going to ignore, right? We're going to ignore this one because it's a hole. It's not an x-intercept. But x equals 3 is going to be our intercept. That means we're going to hit the graph on the x-axis at 3. So our x-intercept would be the point 3, 0. And lastly, we're going to find a vertical asymptote. So for that, we're going to set the bottom equals 0. We're going to factor out a 3x. Now again, we're going to ignore that first 0 because it's a hole. Because it canceled when we originally factored it. Okay? So I get x equals negative 2. So x equals negative 2 is a vertical asymptote, right? It's not a point. It's going to be a line their graph approaches and doesn't touch. I hope this gives you guys a decent start. Do your best. Ask questions tomorrow. I'll have win time open for you guys. All right. Have a good one.